Good evening, this is VK3 EKH, the official station of the Astronomical Society of Victoria, with a regular Friday night broadcast coming to you from the studios of VK3CSJ in Narre Warren South. A very pleasant good evening this 14th of February, and for what it's worth, happy Valentine's Day to those. We're broadcasting on prime frequency of We're broadcasting on prime frequency of 3541 kilohertz in the 80 metre amateur radio band, and also via the Melbourne television repeater VK3 RTV, digital channel 1 in full HT. And we're also streaming direct to my YouTube channel, which you can find at the YouTube, and search for VK3CSJ and look for the live indication. But as I usually say, I highly recommend Discord. If you haven't signed up for Discord yet, go to the website and register. No funds are involved. And then I provide a link on my qrz.com page, either VK3CSJ or VK3EKH. And the link will take you to the chat room and where the HD stream is. And the HD stream, the video stream, is in almost real time. So what you're hearing here on 80 metres is less than a second delay visually on Discord, which is far better than what YouTube offers. So highly recommend Discord. But if all else fails, particularly for tonight, YouTube is the best way, because tonight I'm doing a presentation, replay presentation of Astro Talk, which was done on Wednesday night by the ASVs at the National Herbarium in Melbourne. And it was the presentation by Professor Matthew Bales on fast radio bursts. Most fascinating indeed. And I'll replay it here tonight. It goes for about 55 minutes, then followed by the latest solar report from our Space Weather Woman. And that will tie things up nicely. So I highly recommend that you either tune to the YouTube link, which hopefully will stay up and running for the whole hour, and so you can see the graphics, because the presentation is pretty much fully a slideshow. But Professor Matthew Bales is most interesting to listen to, because he gives you a bit of a history on radio astronomy in as far as the lead up to pulsar research, and then segueing into his research in pulsars and fast radio bursts. So it's a most interesting presentation. All right, so let me just give the usual thing for those that aren't sure what's happening here. Let me see, where's my dialogue? The ASV is a non-for-profit society for people interested in astronomy, attracting and catering for people from a wide range of ages and backgrounds, abilities and interests. First formed 1922, the society has grown to over 1,000 members. In fact, I think it's around 1,800. Its activities are coordinated by a council of elected office bearers, section directors and ordinary councillors. The ASV has weekly activities at our two metropolitan locations, at the Morley Community Village and the Melbourne Observatory. We host monthly Astro Talks at the National Herbarium, which is the presentation tonight from last Wednesday, near the Melbourne Observatory. The Society's library is also located at the Melbourne Observatory and is open during our Astro Talks. For over 50 years, the ASV has played a major role in the care of buildings, the facilities at Melbourne Observatory. Our members conduct astronomy for the people gatherings, a bit like sidewalk astronomy done in America, bringing telescopes and astronomy to Melbourne's parks and schools. For more information about these particular events, you can click on the calendar on the ASV website and see when these events are going to occur, and you can roll up and peer through a telescope. Please check. Yes, I've just said that all. Okay. The ASV is currently involved in a number of major projects We are involved in the restoration of the Great Melbourne Telescope and is currently working on the installation of a series of remote telescopes at the Dark Sky site. And once completed and fully set up, it'll be accessible to members as well. Thanks to a generous donation from one of our long-term members of the ASV, who's no longer with us, who donated the property up there at Heathcote, Ladies Pass, the Leon Mao Dark Sky site, LMDSS, located just north of Melbourne. It has a pristine night sky for deep sky observing. The ASV has a 25-inch telescope, a 40-inch telescope, and a wheelchair-accessible 16-inch telescope at the Leon Mao Dark Sky site, including an 8.5 fully steerable radio telescope, a Kennedy dish, in fact, and makes use of the existing telescopes at the Melbourne Observatory during some extension section meetings at members' nights held once a month at the observatory. There's an annual yearbook, which is applied to members as well, and a bi-monthly newsletter, Crux, called just Crux, which all members are welcome to contribute to. The ASV is governed by a set of rules which should be read before applying for membership. The document apparently is downloadable on the website. Any person or organisation with an interest in astronomy may apply for membership of the Society, and right under that statement is, in big letters, Join Now. Right. Now, again, tonight's session, I'm hurrying up to make a start into this because it goes for a little 55 odd minutes. Vastrock, by the way. This year, ASV is hosting the Vastrock. Save the date, August the 9th and 10th, Vastrock. The Astronomical Society is thrilled to host Vastrock 2025, making the 20th anniversary of this celebrated event. The Victorian Astronomy Convention is a biennial gathering for amateur astronomers across Victoria, held in odd-numbered years. It rotates between different astronomical societies in the state, fostering collaboration and community. In 2025, Vastrock will take place in Geelong, hosted by the ASV's Geelong team. The event will run over 2 days. Saturday, August 9, from 11 a.m. to 8:30 p.m, followed by stargazing at the ASV Geelong club rooms, weather permitting. And then Sunday, August 10, 9 a.m. to 1 p.m, with additional stargazing afterward if skies are clear. Tickets are available from the website here. The event is open to everyone, astronomy enthusiasts, members of related community groups, and anyone captivated by the wonders of the universe. Ticket prices will be announced once the venue and program are confirmed. Vastrock 2025 will feature engaging workshops, thought-provoking talks, captivating displays, and interactive forums. All in a welcoming and social atmosphere. Stay tuned for updates here, or follow the Vastrock Facebook page for latest information. We look forward to celebrating this event with you under the stars. Okay, that information is on the ASV website at www.asv.org.au and under the events tab at the top. All right, let me see. Let's minimize that. All right. Hang on a sec. I was just going to run through about the presentation. Calendar. I'm just reading it from the calendar here. All right. Professor Matthew Bales, in this presentation, will explore the world of fast radio bursts and share with us his knowledge in the field. Professor Matthew Bales is a former Australian Research Council laureate, fellow, and director of the Australian Research Council Centre for Excellence, or of Excellence, for Gravitational Wave Discovery, or OSGRAV. He is a world leader in the discovery and timing of millisecond pulses and has made pivotal contributions to the discovery of fast radio bursts, enigmatic millisecond duration bursts of radio waves that strike the Earth many thousand of times per day and are of unknown origin. In 2023, this was recognised when he was awarded the Shaw Prize in Astronomy. And I'll knock it off there. There is a further presentation afterwards by Bill Stent on what's up in the sky, but that'll take things on a little bit too far. So I'll just knock it off as soon as the presentation is finished. Yep. All right. Let me just queue up this presentation. Where are they? It's in there somewhere. That's it there, of course, right in front of me. Alrighty then. So, like I say, this presentation is very visual. It's got it's a presentation, so it's a PowerPoint thing, and everything that Matthew is referring to, of course, is the slides that he's showing on the screen, which is directly being coupled to the video system. So it comes across in HD and is well presented. So without further ado, it's going to be a bit of a long night. But anyway, hope you enjoy this presentation and hopefully it'll come across reasonably well. You're tuned to ASV Radio, the regular broadcast from the Astronomical Society of Victoria every Friday night here on this frequency and elsewhere. Like I said, we're broadcasting also on the YouTube stream, VK3CSJ. Just type in VK3CSJ, look for the live indicator. And also on Discord, which is the preferred thing because it's, like I said before, the delay between what you're hearing here on 80 meters and visually is just less than a second, which is, if you want to listen to the sound on 80 and watch the video, it works out quite well. Otherwise, on YouTube, it's a 20-second delay. All right, stand by. This is VK3 Echo Kilo Hotel.
Good evening, ladies and gentlemen. For those who don't know me, I'm Chris Rudge and past president. Unfortunately, Mark is sick tonight. He's got a bad migraine, so he asked me to deputise and do the honours for him. So welcome to our February Astro Talk. Tonight we'll hear from Professor Matthew Bales. Professor Bales will explore the world of fast radio bursts and share with us his knowledge in this field. Professor Matthew Bales is a former Australian Research Council Laureate Fellow and Director of the Australian Research Council Centre of Excellence for Gravitational Wave Discovery, AusGrav. He's a world leader in the discovery and timing of millisecond pulsars and has made pivotal contributions to this discovery of fast radio bursts, enigmatic millisecond duration bursts of radio waves that strike the Earth many thousands of times per day and are of unknown origin. In 2023, I don't think you're that old, Matthew. Just feel it sometimes, like the rest of us. In 2023, this was recognised when he was awarded the Shaw Prize in Astronomy. Following Matthew's talk, we'll hear from Bill Stent, the telescope gent, about what's in the sky for February and March of 2025. We have some ASV events coming up. We have our Messier Star Party at the end of the month, the Gippsland Star Party, Inverloch Under the Stars, and also the Mildura Star Party. And if the skies are clear, the observatory will be open for viewing after the talk. Also, our ASV library will be open. Now I'd like to welcome Professor Matthew Bales to the stand.
Thanks very much. I think it's been 7 or 8 years since I gave a talk, so it's well overdue. And I thought I would give a talk about the discovery of fast radio bursts, because I think last time I was here, I talked about gravitational waves. So this is a discovery I was very fortunate to share with my former student, Duncan Lorimer, and his wife, Maura McLaughlin. And we're going to hear a little bit about our journey of discovery. So in astronomy, most astrophysicists are trying to work through the big questions, like what's the size and age of the universe? How many atoms are there in the universe? What laws of physics govern the universe? What types of object exist in the universe? Planets, stars, black holes, neutron stars, quasars. And probably once every 5 or 10 years ago, astronomers tend to come across something that is a new class of object. It's kind of every astronomer's dream to find one of these. So this talk, I'm going to talk about, first of all, our universe, and then the changing radio universe, the discovery of something that's now known as the Lorimer burst, the discovery of the cosmological population of bursts, how some of these bursts repeat, and what you can do with them. So we're used to living on this lovely blue dot in a cosmic ocean, if you like. But most astrophysicists aren't that interested in the Earth or the planets. We're more interested in the night sky and what lies far beyond the Earth. The Sun is just one star in a few 100 billion in our own galaxy, and we think that there's a similar number of galaxies in the universe to stars. Our nearest neighbor galaxies are these guys, the Magellanic Clouds, and they're going to play a part in our story. So there's the large cloud, small cloud, and of course, sitting next to the small cloud conveniently is 47 Tucani. It's been a long journey in understanding our place in the universe. And one of the reasons we understand so much is because of the invention of the telescope. So when we look at Jupiter, Galileo was the first person we know of to point a telescope at Jupiter. And he was amazed to see that it was actually surrounded by its own little planetary system, if you like, of moons. And when he looked at Jupiter, he saw it had companions. I'll turn the labels back on, they're a bit hard to see for you. And that they changed their position every night. And he deduced correctly that they were moons. And he thought if Jupiter has moons and the Earth has a moon, maybe the Earth and Jupiter are more alike than the Earth and the Sun, or Jupiter and the Sun. And so this helped displace the Earth from the center of the solar system and led to us having a better understanding of where we were in the universe. He also looked at Saturn and saw that it had these remarkable rings, although the optics on his telescope were pretty sad. In my professional work, we study the orbits of very compact stars around other stars to understand the laws of gravity. But Mercury, when it was first discovered by the ancients, was seen to have a strange path around the sun. Later, Kepler and Tycho quantified the shape of Mercury's orbit around the sun, and it was pivotal in Einstein's proof that the general theory of relativity was required to talk about the correct trajectory of the Mercury around the sun. We're used to thinking of the Earth as a very large place, but if we could actually place the Earth next to the giant planets, we would actually see that the Earth is actually quite tiny. And this is very important because in the universe, the reason we have the chemical elements is because of stars like the sun actually burn hydrogen and helium, and they are massive chemical factories. And you could actually fit 1 million Earths inside the sun. And we can see that in this nice interactive animation. There's our little Earth over here. There's the sun. We can fit about 1 million Earths inside the sun. But the sun isn't actually very big by astrophysical standards. If we were to put the sun next to a star, say 20 times the mass of the sun, it would actually be quite tiny. And here we can see the size of the sun compared to a star like Rigel, which I'm sure many amateur astronomers are very keen on. And the sun is actually a nice star to live around. It lives for billions of years. But Rigel is a very hot star, and although it's only about 20 times heavier than the sun, it's actually burning energy about 100,000 times faster. So actually look at some critical statistics on Rigel. It's about 20 times the mass of the sun, about 80 times the radius, and the amount of energy coming off a star is proportional to the radius squared times the temperature to the 4th power. So a star like Rigel is burning hydrogen 100,000 times faster than the sun, and will only live for about 10 million years. And when it blows up, it'll leave behind a supernova and also a very compact star called a neutron star. And here, of course, we have the Crab Nebula, a favourite for many amateurs. This is a planetary nebula and a very different end to a star's life. Stars about 10 times bigger than the sun blow up. Ones about the same mass of the sun just peel off their outer layers slowly and leave behind a white dwarf. And with our naked eye, we can't see any white dwarfs, but with telescopes, of course, we can. So how big are these objects? Well, if we were to put a black hole, a neutron star, and a white dwarf together, you would see that the neutron stars are very tiny. This black hole is about 30 times the mass of the sun. The neutron star maybe 1.5. That's about 500,000 Earths. And the Earth is about the same size as a white dwarf. So we could actually fit many tens of thousands of neutron stars inside the Earth. But a neutron star weighs 500,000 Earth masses. We believe that we're in a galaxy that looks a little bit like this one. This is the Andromeda Galaxy, a spiral galaxy with a bulge in the middle and a bunch of satellites. And this is a model of how we think galaxies look. So this particular galaxy, this is a mock-up of the Milky Way. We think there's a bar and these spiral arms. We're about 2/3 of the way out to the edge. And where the active young stars are is actually very thin. So you'll see when we flash past this pretend Milky Way, the disk of stars is very thin. And that's where the massive stars are born. And in our story later on, we'll see where they reside. Some galaxies are kind of boring. Elliptical galaxies don't have the rotation to cause them to collapse into a pancake, and they only have typically one episode of star formation, and most of the stars are red or dead. And then there's the Magellanic Clouds, which are our nearest neighbours. These are what's called very metal-rich, very metal-poor galaxies. They're still undergoing their first round of star formation, and the way stars behave in these galaxies is quite different than the Milky Way, where we've had multiple generations of star formation. And this little guy here is one of my favourite objects in the sky, 47 Tucani, also the home of many neutron stars. We think that the universe is actually made up of filaments of material, and this is a simulation of the large-scale structure of the universe. And in this, whoa, sorry about that. I didn't realise that button meant leave the talk. We'll quickly go back to the universe. And I'll be very careful which button I press from now on. But we think that each of these dots actually represents thousands or hundreds of galaxies. And you can see the structure of the universe. I used to be completely disinterested in anything to do with the structure of the universe because I worked on neutron stars, most of which were in our own galaxy. But as it turns out, I needed to learn some cosmology. So if instead of using an optical telescope to look at the sky, you use a radio telescope, you get a very different view of it. This is the center of our galaxy, and this was taken with the magnificent Meerkat radio telescope. It's 64 dishes in the desert in the northern part of South Africa. And you can see all of these filamentary things. These are actually supernova remnants. And my favorite, I'm sorry to do this to the cameraman, is this little guy here. That's actually a supermassive black hole spewing out material far beyond the Milky Way. The Parkes Radio Telescope is central to my story. I've spent about 2 years of my life observing with the Parkes Telescope, and it's in New South Wales, and it's 64 metres from edge to edge. And up until about 5 years ago, this was the most powerful radio telescope in the Southern Hemisphere and responsible for a large number of discoveries. It was pivotal in working out how the quasars were distributed in the universe, and it actually used a lunar occultation of 3C 273, which was a quasar with the moon, to work out its position on the sky. And then Schmidt from Caltech worked out that the object they were looking at actually had a redshift, and that redshift meant it was one of the most luminous objects in the universe. And it was actually the first discovery of a black hole. So I'm now going to talk about the changing radio sky. And this radio telescope, which doesn't look very glamorous, was actually near the University of Cambridge, and they had built all of these dipoles and wires, and this telescope was phased in such a way that when a radio wave came in, there was a beam on the sky that was in focus. And Hewish was an expert on the interstellar twinkling of quasars. And so he recruited Jocelyn Bell, who was a PhD student, and they did something very unusual in radio astronomy back in the 60s, and that was they removed the integrating time constant in their circuitry, which used to average out all the radio signal. And the reason they averaged out the signal was because they believed there was nothing in the radio sky that would change on short timescales, except for twinkling quasars, which were very small. So Jocelyn's task was to discover more quasars, and instead she discovered the first radio neutron star. So this was her chart recorder. This is a bit of paper. We used to have a pen that used to drawer on the paper, and the paper would go through maybe a few centimeters per hour, and you would map the radio sky by looking at how your chart record went up and down. This is an inverted scale, so going down is actually stronger. And she discovered the first neutron star. So the time between these little bumps that are regular here is actually 1.33 seconds. And this was the discovery of the first pulsar. It used to be called CP 1919, Cambridge Pulsar 1919. And it was discovered when I was only 4 years old in 1967. And Jocelyn is still alive, and she actually gave a talk at the most recent pulsar conference I went to in Italy. And this was a picture of her after they'd announced the discovery of pulsars, which were basically pulsing sources of radiation. Unfortunately, when you make a discovery in science, there's no manual that tells you what it is. So they had to deduce whether this was a rotating white dwarf or a pulsing object or indeed a neutron star. And neutron stars were still very much theoretical conjectures at the time. So shortly after Jocelyn found her pulsar, others were found in the Crab Nebula, and the giant Arecibo telescope was used to scour the sky to look for more neutron stars. So this is our current model of a pulsar. It's an object only about 20 kilometers across. They rotate, their rotation period, the fastest one rotates every 1.4 milliseconds. So that's about 700 times a second. So you've got something about the size of the city of Melbourne rotating 700 times a second, which I can't do on this screen, but this particular pulsar is spinning maybe once every couple of seconds. That would actually be a very slow neutron star. Some of them, however, have slowed down to very slow rotation periods and only spin every few minutes. They have amazingly strong magnetic fields. They weigh between about 1.3 and 2 solar masses. And the density of a neutron star is such that a cubic centimeter, like a teaspoon, weighs 1 billion tons. There's now actually about 4,000 known, and most of the ones we know of live in our galaxy. And what we think is happening is that the magnetic field acts as a particle accelerator, and the accelerating particles in what's called the magnetosphere radiate radio waves, and we get a beam of radio emission. And if that beam crosses your line of sight, you get a pulse. And so Jocelyn was fortunate enough to discover 4 of these in her PhD. What they soon discovered when they were looking at these pulsars is that the radio waves coming from the pulsars didn't arrive at the same time at all radio frequencies. And we understand the reason for this, and that is that if you're a radio photon, when you come across an electron, you actually experience a time delay. And that time delay depends on your radio frequency. And so the time at which you arrive at the telescope is later for the red photons than they are for the blue photons. And this is an observation with the Meerkat radio telescope. And if I come over here, I'll look down, I see a beautiful mathematical relationship between the time delay and the when the pulse arrives. So this is about 400 milliseconds of time. At 1.5 gigahertz, the pulse arrives, and then it sweeps down and takes longer and longer to arrive. And about 400 milliseconds later, it arrives at the lowest frequencies. If we straighten this up by a process we call de-dispersion, we see the original pulse, which looks a bit like that. So we can use these what's called dispersion measures to actually work out where all the neutron stars are in our galaxy. And this is a model of our galaxy and where the neutron stars live. And the color of these dots reflects their dispersion measure. So red dots have small dispersion measures and blue dots have very large dispersion measures. And the sun is actually in that ball of pulsars. And so you might think, why on earth would the sun know to live in the middle of a bunch of pulsars? So it's in this little bunch here. And that's what we call a selection effect. So it's actually really easy to discover a pulsar if it's nearby. But because of the inverse square law, as they get further and further away, they get harder and harder to detect. And so we knew, as pulsar astronomers, that it was impossible to have what's called a high dispersion measure if you were off the plane of the galaxy, because there just weren't enough electrons. So these radio pulses, as they travel towards the Earth, they get a bigger and bigger dispersion because they're basically an electron counter. And so we knew that off the plane of the galaxy, everything was red, but in the plane of the galaxy, things could be blue. So if we were searching for pulsars, we had to search in both position but also dispersion. Now, we knew it was kind of silly if you were looking outside the plane to look for high dispersions because you ran out of stars. So in the 1970s, instead of using chart recorders to find pulsars, people started using computers and using this wonderful thing called the Fourier transform, which can take a very long observation and tell you if there's anything periodic in it, like a pulsar. And so Joe Taylor and Russell Holtz discovered the first binary pulsar, and the binary pulsar had this nice property that it was going around another neutron star, and instead of taking a year to go around its other star, it actually did it every 8 hours. And because it was going around so quickly, there were a whole host of relativistic phenomena that, because of the bending of space and time, that meant that Taylor and Holtz ultimately received the Nobel Prize for Physics by proving that every time these stars orbited each other, the orbit shrank by 3 millimeters in orbit. And that was due to the existence of gravitational waves. But that's another whole talk. So we used to fantasize about maybe being able to see pulsars in other galaxies. And the Crab pulsar actually had this habit of giving off not just regular feeble pulses, but every now and then what's called a giant pulse. And so it was thought that if you could put the Crab pulsar in the nearest galaxies, you might be able to see it. So Maura McLaughlin and Jim Cordes, a couple of friends of mine, used this big 300-meter telescope to look at other galaxies to see if there are any so-called giant pulse emitters in there, and they found nothing. However, Maura thought, well, if I can't see anything in other galaxies, what if I try our galaxy? And she discovered a new class of neutron star that seemed to have no periodic emission, but would occasionally give off a giant pulse. And these things were called the rotating radio transits, or RATs. And it was deduced from a population study that maybe there were as many of these things in our galaxy as pulsars. So they used to have this little computer program that would search their data in time, and if a giant pulse occurred, they could measure its dispersion. And if there were a real source came along, it would rise in what we call signal to noise, then drop off again. And they could deduce the dispersion, how many electrons there are between us and the pulsar, or how curved that arrival time was at various times. And this was an observation of a new rat, which had 3 major pulses over the course of half an hour. And if you looked out at our galaxy, and you said, where are these rotating radio transients? I've done them in the big blue dot, big red dots. So most of them were near the plane of our galaxy. And if you can see down the bottom here, there's actually a bump, a cluster of pulsars. They're actually the pulsars in the Large Magellanic Cloud and the Small Magellanic Cloud. And so Duncan and Maura, my colleagues, had the idea to look for these rotating radio transients in the Magellanic Clouds. So they got data from the Parkes telescope, and they plotted a timescale versus luminosity for everything we knew about, And unfortunately, they found that even the brightest, most luminous, what they call rats or giant pulsars, were almost invisible if you put them in the Magellanic Clouds. But they thought they'd have a shot at trying to see them anyway. So this is Duncan when he was younger and more beautiful. That's him with his wife and their firstborn child, who's now at university. And they got data from a survey of the small Magellanic Cloud, and they looked for these rats with the help of summer student David Narkovic. So Frony Crawford had done a survey of the small cloud using something called the Parkes multi-beam receiver, which had 13 patches of the sky it used to look at once. And they'd discovered a bunch of pulsars, and they were searching for these rats as well. So this is an example of the brightest neutron star in the Magellanic Cloud, and you could see every 1,000 seconds or so, or maybe a few hundred, it would give off a pulse that was marginally detectable. And then Dan found that there was this incredibly bright burst at a very high dispersion in his data, but he didn't know what it was. And so I happened to be at the Parkes Radio Telescope with Duncan, and a month or two after his student had found this apparently high dispersion pulse, I asked Duncan if he'd found anything interesting lately. And he said, well, I had this pulse he couldn't understand. The pulse was a bit unusual because instead of just appearing in one of the 13 beams, it had actually occurred in two. And he had trouble understanding that. And I said I had some lovely software that could plot what's called the waterfall plot of radio data. And so we took the data from these two beams, and we were astounded to see this beautiful sweep. And if you, sorry, cameraman, but if you were to look along here, you would see this has a beautiful mathematical relationship of delay versus time. So this is a plot of the intensity of radio emission. There's lots of noise and crap. But then there's this beautiful sort of sweep. And that sweep was because a very bright radio pulse had hit the Parkes telescope. And instead of just appearing in one beam, it had actually occurred in two. And then we realized that it was actually in a third beam, but our software had decided that was so ridiculously bright, it couldn't possibly be real. So what had happened was we had a 1-bit digitizer in our electronics, and when the burst hit, it saturated the system and everything just went off afterwards because it had raised the mean level. And our software was so clever, it decided, well, that's obviously interference, so it deleted it. But we were lucky to still have this data on tape. And when we reprocessed it, we were astonished to see this bright burst. And this was what we call an 100 sigma event. So you can normally detect things above about 10 sigma in a radio telescope, but this was 100. And this was remarkable, and it became known as the Lorimer burst. And when we calculated how far away it must be, we realized that it was actually so far beyond the Magellanic Clouds that it had been traveling for about 1 billion years. And the idea was that when the burst first left its source, it had no dispersion delay because there were no electrons. As it left the host galaxy, it slightly increased its dispersion. And then it flew throughout the universe for 1 billion years, coming across electrons every day. And by the time it hit the Milky Way, it had this high dispersion measure. And so this was quite amusing for me because I'd never even thought about doing radio astronomy on sources in distant galaxies. We thought it was almost impossible to detect them in the nearest galaxy. And when we plotted the luminosity of the Lorimer burst against all known objects, it was 12 orders of magnitude brighter than anything we'd ever seen in the radio sky. And so this was cause for a massive celebration, and I couldn't sleep the night we discovered this because I thought maybe this is a new class of object and maybe it was going to make us all famous. and the burst was only 5 milliseconds in duration. So at any one frequency, it only lasted 5 milliseconds. But because of this dispersion sweep, it actually took over 300 milliseconds to sweep past the telescope. And this data was actually about 6 years old. So it had been sitting on magnetic tapes, kind of ignored and unloved. So we weren't sure what it was, but we wrote a paper on it. We actually submitted it to Nature and it got rejected. And we submitted it to Science and they loved it. So we said, we've analysed archival survey data and we've discovered a 30 Jansky, that's a measurement of strength in radio astronomy. It actually means 30 by 10 to the minus 26 watts per square metre per hertz, which is not very much. It was 3 degrees from the small cloud, and the burst properties argue against a physical association with either our galaxy or the cloud. And we looked at it for another 90 hours. I went back to Parkes, pointed the telescope at it, didn't see anything. And so we postulated that maybe it was from a supernova or something that coalesced. And hundreds of these things could happen every day. And if we could detect more, we could use them as cosmological probes. So the problem with the Parkes telescope is it actually looks at less than a square degree of the sky. So the idea was these things are happening everywhere, but we just can't see them. So we weren't sure what it was. It was very energetic. It was about the same amount of energy that the sun gives off in a month in 5 milliseconds. It was very narrow, so light travel time meant it was probably less than a few thousand kilometres in diameter. So we weren't sure if it was a neutron star, an interplanetary radar, supernova, or 2 coalescing neutron stars. It soon entered popular culture, and this is a band called the Lorimer Burst, which I really love, and their title track is Dispersion. We also appeared in a book about serendipitous discovery. So we were keen to find more, and I had a student, Sarah Burke-Spalor, who's now a professor in West Virginia, and she contacted me one day and said, I found another burst. I went, yes, awesome. And she showed me the burst, and it didn't look quite as nice as the one we had seen. It was all kind of patchy and blobby. And then she found a whole lot more that looked very similar, and that was a little bit disturbing. And not only did they look similar, they actually appeared in all 13 beams of the receiver. And that means they're in something called the Fresnel zone, which means they must be originating from something within a few kilometres of the dish. And so some of them were blotchy, some of them looked a little bit better, some of them had funny kinks in them, and we didn't know what they were. It took another 5 years before anybody found one that was even remotely convincing. This is Evan Keane, a former postdoc of mine. And if you look at this one, yeah, it looks pretty good. But unfortunately, his was right in the plane of the galaxy, and we couldn't tell whether it was behind the galaxy or in it. So it might have just been a pulse from our galaxy. Then my colleagues and I decided to look at the whole sky with the Parkes telescope. So we built a whole lot of supercomputers and digital electronics, and we did a survey of the entire sky for 4 minutes, the inner part of the galaxy for 15, and the middle part for over an hour. And we discovered a whole bunch of pulsars, but we didn't find any Lorimer bursts. And then one day, Dan Thornton, who was a PhD student of Ben Stapper's, who was my former student, and now working in the UK, sent us an email saying he'd found a very bright fast radio burst. And it's amazing, once you found one, he soon found another 3. And we wrote a paper announcing the discovery of the cosmological population of fast radio bursts, again in the journal Science. And this was our best one. It was incredibly bright, and it had a dispersion that meant it was 3 times further away than the Lorimer burst. And in fact, it seemed to be coming from such a great distance that the universe was less than half its current age when it left. So if you actually plotted galactic latitude, how many degrees off the galactic plane, versus the dispersion measure, the pulsars do this nice envelope-y thing. This is like along the galactic plane, there's lots of electrons, off it hardly any. These little bunches here are the small cloud and the large cloud pulsars. And these were our, what we now called fast radio bursts. Fortunately, the Americans found one with their giant telescope. And at Parkes, we kept finding them every month or two. Some of them had dual structure. Some of them were quite weak, some quite strong. And this guy here was astonishingly bright and appeared in nearly all of our beams, but especially bright in one of them. And this was just an accident that happened while we were observing a pulsar. We built a new system at the Molonglo radio telescope and discovered a way to get very high time resolution. And we could show that the bursts were actually comprised of little microbursts. And then John Sarkisian discovered that if you opened the microwave oven at the Parkes control room, it let off something that looked a bit like a fast radio burst. And so we understood the origin of at least some of those ones. The first one the Americans found was actually observed a lot because they couldn't find any others. And they discovered on one of their repeat visits another 8 bursts, I think it was. 11. And some of them were ridiculously bright. And the next time it went into a sort of repeating mode, they localized it with the very large array to its host galaxy. And they could actually work out the redshift of the galaxy and found the host. And the host galaxy was this tiny little galaxy about 1/10,000th of the size of the Milky Way. That's it there, inside that red circle. It was an incredibly magnetic object. And this little micro galaxy, if you want to call it that, had a very high star formation rate. And so we believe that these probably came from neutron stars in what was called these very low metallicity clusters. They found that the repeats seemed to happen with a period of about 157 days. And another one was found that seemed to repeat every 16 days. And so this is our model of what might be going on. There's some big star with a disk of material, and maybe we can only see the fast radio burst when we're on one side of this disk. And there's various other characteristics of the dispersion as the neutron star probably orbits its other star. But this is only a model. So nowadays, more than 8 telescopes have discovered fast radio bursts. One was even found in our own galaxy with a radio telescope only 20 centimeters was in size, which was remarkable. And this occurred at the same time as something called a magnetar. That's a very magnetic neutron star, had what's called a flaring event. So magnetars have a role in the emission of fast radio bursts, maybe all of them. And at the moment, the Canadians have built this remarkable telescope that seems to find a fast radio burst every few days. But sadly, they also found one in a globular cluster in a nearby galaxy, which is only 3.6 megaparsecs away. And if they're coming from young neutron stars, you don't expect to see them in globulars. So there's still a few mysteries there. There seems to be different classes of fast radio bursts, those that repeat and those don't. And our friends in Western Australia used the telescope called ASCAP to actually trace the origin of many fast radio bursts. And most of them seem to come from young star-forming regions in galaxies, but a few are coming from ellipticals. These are where all the fast radio bursts that have ever been detected are coming from. The green dots are because of that CHIME telescope, which monitors all of the sky, or the northern sky every day. And you can actually use fast radio bursts to count the number of electrons in the universe by plotting how much the redshift of the galaxy is versus what the dispersion is. And then you get an electron count. In the future, we think you'll be able to use them to measure the Hubble constant. And most recently, Stuart Ryder et al. Detected one that could be traced to a galaxy with a redshift of 1. So that was the light has been redshifted by its entire wavelength. And if you now populate this diagram of timescale versus luminosity, this was the original Lorimer burst. And we've filled in all this area of phase space and have a brand new area of astrophysics. So there's lots of open questions. I'm not going to go through all of them. But I did want to thank my colleagues who helped us discover these remarkable objects, all the institutions that support us. And as a happy ending, we were awarded the Shaw Prize, which is a bit like the Nobel Prize for astronomy, a couple of years ago. So there's Duncan, who's my first ever PhD student, his wife Maura, that's me. This is Reinhard Genzel, who's a Nobel laureate who handed out our checks for $600,000 and our gold medals. And then fortunately last year I was awarded the Prime Minister's Prize for Science, partly for the discovery of the fast radio burst. So I'll stop there and ask for questions.
Well, thank you very much for that. I think I'll have to go back and check the recording to get some more, take in all that information. Do we have any questions from the floor? You've boggled them all, Matthew.
Are there any leading theories about what they may be?
Yes, we know that at least one of them came from what's called a magnetar in our galaxy. Magnetars tend to have a magnetic field about 100 times bigger than an average pulsar. And then magnetic fields seem to be quite unstable and they sort of glitch and reconnect. And it's thought that during those episodes, there's a burst of radio emission that takes some of the magnetic energy and turns it into radio energy. So we know at least one came from a magnetar. All the others are speculation. But there are some properties of the polarization of the radio waves that we receive that makes us believe that we're looking at something in a very intense magnetic field. And really the only place in the universe that has very intense magnetic fields are neutron stars.
Thank you for that.
Okay, I think I'll leave it there. This is VK3 Echo Kilo Hotel, the official station of the Astronomical Society of Victoria, Astronomical Society of Victoria. I hope you enjoyed that presentation by Matthew, Professor Matthew Bales. That was done live on Wednesday night at the